Hi, in the third module start. Third module deals with the uniform convergence. So we start with the definition of uniform convergence. So suppose we have a sequence of functions, sequence fn. These functions should be defined on a common domain. So if we start with fn's defined on a common domain E, which is a subset of real numbers, to R. So these are the sequence of functions defined on E. Okay, so real valued functions. So we have for n is equal to 1, 2, 3, etc. So this is called the sequence of functions, and it is denoted by sequence fn. Now suppose we have x0 belongs to E. If we choose an x0 from E, then we can evaluate f1 of x0, f2 of x0, f3 of x0, and so on. In fact, these are the real values because this is a function from E to R. Then for each x0 belongs to E, fn of x0 should be an element of R. So this will give real numbers. Say a1, we call it as a1, a2, a3, etc. Okay, so this is a real sequence. Suppose this real sequence converges. Okay, converges to some point L0. We call that if it is convergent, then it has a unique limit, say L0. Now we take another element x1 from E and consider the real numbers f1 of x1, f2 of x1, f3 of x1, etc. So corresponding to x1, we can construct a sequence of real numbers. So this may not be same as the previous sequence, so we denote it as b1, b2, b3, etc. Suppose again that this is also convergent, so we can get a unique limit, say L1. Now we collect all the elements from E and construct such real sequences, and suppose that all those sequences are convergent, then corresponding to each x0, x1, x3, x2, etc. belongs to E, we can get a unique numbers called L0, L1, etc. Okay, so corresponding to x0, we can get an element L0. Corresponding to x1, we can get an element L1, and etc. Okay, so this would enable us to define a new function f from again E to R. Okay, and it is denoted by these rules, that is f of x0 equal to L0, f of x1 equal to L1, and so on. If this is possible, we can say that the sequence of functions, sequence fn, converges to the function f. So this is a sequence of functions, and this is the limit of the sequences of functions fn. Okay, this is convergence of a sequence. Okay, this is uniform convergence. Okay, so first of all, we need to verify the convergence of a sequence of functions. Okay, so suppose there exists an element, say some xr, such that fn of xr is not convergent. If this is the case, if there is at least one xr such that fn of xr is not convergent, then the sequence of function fn is not convergent. Okay, for any x belongs to E, the sequence of real numbers fn of x should be convergent. Sequence of functions converge in sequence point in convergent, we will say that this sequence of fn is not convergent in the okay. This is sequence of fn in the convergence, and this convergence is called point-wise convergent. Point-wise convergence. So we can define point-wise convergence in such a way that let x belongs to E, limit x tends to limit n tends to infinity, fn of x equal to f of x. for each. Okay, so this is the convergence of sequence Fn. This is what we called the pointwise convergence. Okay, now we define the uniform convergence. So if this is the case, if Fn converges to F pointwise, then for each x0 x1 belongs to E, we have this type of convergence. Okay, so if you verify the convergence of the first sequence, we can say that for every epsilon greater than 0, Fn of x0 converges to F of x0 or L0. This is our notation. Fn of f of x0 equal to L0. This is our notation. So if this is the case, then corresponding to each epsilon greater than 0, there exists some n0, okay, such that Fn of x0 minus L0, modulus of this can be made less than epsilon for all n greater than or equal to n0. So this is the definition of this sequence. Okay, so corresponding to, if we set the same epsilon here, then we can get corresponding to the sequence Fn of x1, which converges to f of x1 with our assumption, which is equal to L1. We can get there exists some other stage, because this is entirely different sequence from Fn of x0. So there exists another stage n0, n1, such that modulus of Fn of x1 minus L1 less than the same epsilon for all n greater than or equal to n1. Okay, so if E contains exactly 2 points, then you can get the maximum of this n0 and n1. Then you can fix a common n. Okay, which corresponding to that n, we can expect these two conditions. Okay, these two conditions hold for those particular n. If there exists another x2, then you have n2 such that if E contains another point x2, then we have Fn of x2 minus L2, which is less than epsilon for all n greater than or equal to n2. If E contains exactly 3 points, x0, x1, x2 മാത്രമേ ഉള്ളെങ്കിൽ, you can choose the maximum of this n0, n1, n2. Then if you set that n as the maximum of n0, n1, n2, then you can expect these three conditions hold for the corresponding n. So we can get a common n. Okay, so we are searching for such common n. If we choose all such x1, x2, x3, etc., and can we get a common n? That is the definition of the uniform convergence. Or can we get a uniform n irrespective of these points? Okay, so that means that can we get a common n applicable for all these points, x0, x1, x2, etc. Okay, for all points in E. If we get such n, then we can say that this pointwise convergence is uniform convergence. That means if we get epsilon greater than 0, if a pointwise convergence holds, then corresponding to each x0 we can expect n0. Corresponding to x1 we can expect n1. Okay, so corresponding to each x belongs to E, we can get some n depending on that x. Okay, so if we get corresponding to epsilon greater than 0, there exists n such that Fn of x minus f of x, okay, less than epsilon. In fact, this L0 is our f of x0. This is f of x1. In our notation, this is f of x2, and so on. So can we get, corresponding to this epsilon greater than 0, can we get n such that Fn of x minus f of x less than epsilon for all n greater than or equal to n, and for all x belongs to E. If this happens, we can say that convergence is nothing but uniform convergence. Okay, so the only difference between pointwise convergence and uniform convergence is if we fix an epsilon, corresponding to pointwise convergence, you can get corresponding to each x there exists a stage n0 or a particular real integer, positive integer n0. x1 corresponding to x1 we have n1, corresponding to x2 we have n2. That means these n depends, not only this epsilon depends on each x. Okay, if this x varies or x1, x2, x3 varies, then this n1, n2, n3 varies. Clear? So corresponding to each epsilon and a point x, we can get a stage. Or if we are considering uniform convergence, you can expect corresponding to each epsilon there exists a stage irrespective of the point. That means this stage does not depend on the points that we have chosen for constructing this sequence. Okay, so this is the difference between uniform convergence and pointwise convergence. Okay, now we can discuss an example. First we take fn of x defined as x raised to n, and the interval x belongs to closed interval 0, 1. These are famous functions. F1 of x is our line, x belongs to closed interval 0, 1. F2 of x is parabola, x belongs to x, and so on. F3 of x equal to x cube and x raised to 4, etc. These are the polynomials. So we can easily draw the graph of these functions. Okay, so this is our 1 and this is again 1. So the graph of f1 is this. Okay, graph of the x, we write it as this is the graph, and graph of this is the graph of f1 of x, and this is the graph of f2. F2 is a parabola, so we have graph like this, and x cube we have graph like this, f3 we have the graph like this, and f4 we have graph like this, and so on. Okay, so this is f2 and this is f3, f4, f5, and so on. Okay, now what is the meaning of pointwise convergence here? If you fix, this is our domain, so if you fix a point 0, if x equal to 0, then you can get f1 of x. Okay, what is f1 of x? If x equal to 0, f1 of x equal to x raised to n, that is equal to 0, then you can get this sequence singleton set 0, 0, 0, so which converges to 0 itself. So we define f of 0 equal to 0. This is the definition of the limit function. Okay, now we start with 1, then the corresponding sequence fn of x equal to x raised to n, that is equal to, since x is equal to 1, that sequence is 1 raised to n, that is 1, sequence 1 itself, and again it converges to the same point 1. In that case we define f of 1 is equal to 1. If we choose any x in between 0 and 1, we can construct the corresponding real sequence, that is x raised to n, that is the sequence x raised to n again, that is x raised to n, which converges to 0. Since this x is less than 1, then as n tends to infinity, this sequence tends to 0, so we define in that case f of x equal to 0. So this defines a function such that when x equal to 1, the value of the function is 1, and all other values 0 less than or equal to x less than 1, we have 0. So we can say that sequence fn converges to f of x. So this is the pointwise convergence of the sequence. Okay, so what is the geometrical meaning of this? If you choose 0, then f1 of 0, f2 of 0, f3 of 0, everything is 0. So the sequence is 0 sequence which converges to 0. If you consider 1, then f1 of 1 is 1, f2 of 1 is 1, etc. Everything is 1, then that sequence is 1, so converges to 1 itself. Now we take any x in between 0 and 1, then f1 of x is this one. Okay, this is f1 of x, and what is the other point? f2 of x. f2 of x is this one, f2 of x. f3 of x is this point. f4 of x is obtained from this point, and so on. So we can say that these points converges to 0 as n tends to infinity. That's why we write this f of x equal to 0 for x is less than 0 is less than x less than 1. So this is the geometrical meaning of pointwise convergence. Now we verify the uniform convergence. How will you verify the uniform convergence? In order to verify the uniform convergence, we consider epsilon greater than 0. Okay, for epsilon greater than 0, we need to get fn of x. We need to get a particular state such that fn of x minus f of x less than epsilon. Okay, less than epsilon. So we are expecting this result. This is true for every x and every n. So what is the meaning of this? When you remove this or unfold this modulus, then we can get f of x minus epsilon less than fn of x less than f of x plus epsilon for all n greater than or equal to n and for all x belongs to closer to 0, 1. Okay, so what is the meaning of this? When you consider f of x is this function. So if you construct a function f of x minus epsilon and f of x plus epsilon, so that will be like this. If we consider this is our f of x plus epsilon, and we consider this is our f of x minus epsilon. At this point we have this strip. At 1, this is f of x minus epsilon and this is f of x plus epsilon. Okay, now you consider a particular stage and capital N such that for all n greater than or equal to n, can we consider this f of x minus epsilon less than fn of x less than f of x plus epsilon for all x belongs to this. That means the graph of every fn of x after this capital N, we should expect the graph of these functions lie inside these functions f of x minus epsilon and f of x plus epsilon. That means if you consider this particular stage capital N, then we expect these functions f capital N plus 1 and plus 2. We need to get all the graph of these functions should lie in this strip. Okay, this is f of x plus epsilon, this is f of x minus epsilon. But when you consider any function in the sequence, that function starts from this and come to this way, and when the x approaches to 1, this function approaches to 1 itself. Okay, so that means if you consider any function fn of x, we never get the graph of that function is fully contained in this strip. Okay, that means we can never expect a stage which satisfies this condition. Okay, which shows that the convergence of these functions, this sequence of functions, is not uniform. Okay, so this is the exact meaning. The exact geometrical meaning of the uniform convergence is if you consider sequence of function, in order to get the uniform convergence, you fix an epsilon greater than 0. Corresponding to this epsilon, you need to get a stage n such that the graph of fn of x after this n should lie in between f of x minus epsilon and f of x plus epsilon. Okay, so if you are aware of this limit function, this is what we call the limit of fn of x. If you are aware of this limit function, then construct two functions f of x minus epsilon, f of x plus epsilon, and find a stage capital N such that the graph of fn of x after this capital N should lie on these two functions, f of x plus epsilon and minus epsilon. Okay, so this is the geometrical meaning of uniform convergence. Okay, next class we will discuss the Cauchy criterion for uniform convergence and some characterization for uniform convergence. Okay, after that we will discuss what is the relation between what is the connection between uniform convergence and continuity, uniform convergence and differentiation, and so on. Okay, thank you.